Hello, everybody. Welcome to Maths Makes a Difference. This is our first webinar in this series. We are looking today at how we can use mathematics to make predictions to help our lives. We are super excited to be joined by so many of you. We're really looking forward to working with you on some maths today. Just to let you know, my name's Vicky. I teach maths to undergraduates in Oxford, and I work on public engagement with maths and outreach in various ways and with various people, one of whom is Claire. Let me hand over to Claire.
Hi, I'm Claire. I work with Enrich, and I also work with the STEP Support Programme, and I'm based in Cambridge.
And behind the scenes, although you can't see, are Charlie and Marilee from Enrich and from Oxford, who are helping with all sorts of practical things behind the scenes, plus also various people who've helped with planning this and getting it all set up and all the rest of it. We are super excited to be joining you.
What I want you to do is I want you to imagine that you're the ice cream buyer for a group of supermarkets. It's the end of February, but you need to actually work out how much ice cream you're going to need to buy for the May half term. Excuse me. So in 4 months' time, it might be a really, really hot May Day bank holiday, or it might be wet and disappointing. And actually, you're going to want to buy more things like hot chocolate and that sort of thing. So we need to know what the weather's going to be like in 4 months' time. Lots of other things need weather forecasts as well. So gritters, councils need to know how much grit they might need to order for the winter. Hospitals need to plan for whether it's going to be a really cold winter. And people who are looking at holidays might need to think about where might be warm, where they might want to go. So prediction is really important, and it's not just the weather that's really important for prediction. We've all seen recently how important prediction is to all our lives. We're also doing things like predicting climate change, how much the temperature is likely to go up over the next 50 years. And prediction can also be quite hard, and I'm going to pass back to Vicky to talk a little bit more about that.
Thanks. So yeah, prediction's really important, but also it could be hard. And what we want to do in this session is explore with you a little bit about the mathematics behind that. So how can we use maths to help with prediction, but also why can prediction sometimes be hard? And we've got an example. A couple of weeks ago, on the 14th of January, the BBC weather team published a really interesting story. They'd noticed some particular atmospheric things going on in the stratosphere, way up in the atmosphere, which might lead to, they were asking, could there be another beast from the east, a really cold spell? And the story was explaining the weather phenomenon that they're seeing and why that might happen, but also mentioned that it's really hard to know for sure that far out. So they're talking in the middle of January, they're looking at behavior at the end of January, early February, when they're predicting there might be this cold spell. And the BBC story said until these effects they observed in the stratosphere filter down into the lower atmosphere, computer models will struggle to accurately predict our surface weather in the coming weeks. And even once this does happen, small errors in the forecast simulations could result in very different weather a few days ahead. So we want to be thinking about the predictions, but also where are these small errors? Why could they result in very different very different weather a few weeks ahead? We would love to work with you on predicting the weather, but it turns out predicting the weather is really hard. It uses some university level maths and probably a supercomputer too. So we are not going to do that now. What we want to focus on instead is a slightly different aspect of prediction that illustrates some of these same things so that we can get you involved with doing some of the maths. And Claire's going to talk a little bit more about that now.
Yeah, instead of modelling the weather, we're going to look at modelling the population of a creature. Now, for this webinar, we've made up a creature, which we've called the quizzle. And we're going to look at how we might model the population of the quizzle. We're going to look at a system of equations where the population of the quizzle next year depends on how many quizzles there were the year before. So we're assuming it works on a year-long cycle. So it might have one family of baby quizzles per year. We're going to start by using a fairly straightforward model for this population of quizzles. We're going to look at one single equation where the number of quizzles next year just relies on the number of quizzles that there were the year before. And then we're going to look at that repeatedly. So if the number of quizzles this year is twice the number of quizzles the year before, then the year after that it might be 4 times the number of quizzles. I think I'm going to pass back to Vicky, to ask her to show us the first equation we're going to look at.
I'm trying not to be upset at the idea that I might resemble the quizzle on the screen at the moment. So let's have some notation to help us write down an equation so that we can model the behavior of these quizzles. And as Claire mentioned, we're going to start simple and then we can kind of build up. This is what often happens with mathematical modeling. So we are going to write y subscript n for the number of quizzles in year n. So if you imagine we start in y0, so y0 is how many quizzles there are at the start. If there are 1,000 quizzles at the start, then y0 equals 1,000. And then we keep going, counting through the years. So if there are 700 quizzles in year 3, then y3 is 700, for example. So hopefully that helps you get used to the notation that we're going to use here. And what we want to do is write down an equation that captures how the population of quizzles evolves over time, as Claire says, sort of iterating on a yearly basis. And if we imagine that the number of quizzles in one year is proportional to the number of quizzles in the year before, that seems like quite a good assumption. If you start with lots of quizzles, you expect lots of baby quizzles, you expect lots more quizzles the next year. So a good starting position for a model might be to predict that yn plus 1, the number of quizzles in year n plus 1, is k times the number of quizzles in year n, so k times yn. What is k? It's just some constant that represents the, I guess, the biology of the quizzle. So how many babies a typical quizzle will have, that kind of thing. So k would be some kind of constant dependent on the particular species that we're looking at. And then we can just iterate this each year. So we start with some number of quizzles, the next year there are k times that, the next year there are k times that, and so on. And that sort of seems like a good model until you stop and think about it a little bit more, when you realize that potentially, if k is 2, for example, you just keep doubling the number of quizzles every year, eventually you're going to end up with the whole surface of the Earth covered in a kind of carpet of quizzles. This is not a realistic model, because in reality, the environmental constraints will mean that the population is capped. It can't just keep doubling forever. So what we need is some kind of more sophisticated model that says, well, maybe there's this kind of proportional growth, but also at some point they're going to run out of space, habitat, food, whatever it may be. We need to take that into account. So Claire's going to talk about that.
Yeah, so it turns out that actually it's a good idea to, instead of model the number of quizzles, we model the proportion of a theoretical maximum number of quizzles. So we might work out that there are, theoretically, we could support 1,000 quizzles overall, and we look at the proportion of that maximum number. So if Vicky could show the next slide, we're going to use xn to stand for the proportion of the maximum number of quizzles possible that there are in year n. So if x3 equals 0.5, it means that in year 3, the number of quizzles we have is half of the maximum possible population. So if the maximum possible was 1,000, this would mean in year 3 we had 500 quizzles. So we're saying that we don't want the number of quizzles to just keep increasing until it's covered the entire Earth. So we're going to change our equation a little bit. So if Vicky could show us the next slide. We're going to use the proportion of the maximum is equal to k times proportion this year, which looks just like the equation we had before, but we also have this 1 minus xn term. Now, when the number of quizzles gets really close to the maximum possible number, that means that xn is getting really close to 1, then that 1 minus xn term gets really small, and that works to dampen down the population again. So it could be that if you have a quizzle explosion and they're all over the place, that they start competing for food and more start dying of starvation. Or it might be that if you have masses of quizzles, there's then a rise in the number of quizzle eating animals that start eating lots of quizzles. and so lots of them start disappearing. So this sort of contains a bit more of a realistic view. So if we're actually going to use this first thing I will say is that biologists did use this equation back in the 1950s. There were several biologists using this to model populations of fish and other creatures. Nowadays, if we're trying to model the population, we'd have more sophisticated equations. We'd have things linking in what's happening to other animals. We might have a more continuous and smooth equation rather than a lumpy next year, just depends on what happens with this year. But even with this fairly simple equation, we can still get some interesting maths out of it. Okay, so I'm going to hand back to Vicky now.
So what we would really like is for to start having a look at how this works out with some actual numbers to get a little bit of a feel for what happens when we are using numbers in this kind of set situation. So if you've got a calculator to hand, you might want to grab that. Don't worry if you don't have a calculator. This isn't going to be the whole session. We will use a calculator for a little bit and then move on to something else. But if you've got a calculator to hand, grab it now. Claire's going to demonstrate how you might use a calculator to go through and apply working out some numbers from this equation, predicting how the population of quizzes evolves.
So I'm hoping that everyone can see my calculator. I'm going to look at the population where the k, the constant, is equal to 1.5. So we know that xn plus 1 is equal to 1.5 times xn times 1 minus xn. My initial population I've chosen is going to be 0.2. So I'm going to type in 0.2 and enter. Then what I can do is I can use the calculator to actually perform an iteration for me. So what I can do for my next answer is if I type in 1.5 times answer times 1 minus answer, it will take my previous answer and iterate it for me. So this is going to tell me that in year 1, the proportion of quizzles is 0.24. And then in year 3,
Claire, sorry, can I just
yes,
can you just move your paper down a tiny bit so we can see
yeah,
the equation at the top? Perfect.
There we go. In year 2, the proportion would be 0.2736, and in year 3, and so I can just keep pressing enter, and it will just keep working through all the proportions each year for me. So you can see that in year 3, we've got about 0.3% of the total population, not 0.3%, 0.3 of the total population. Okay, I think that's all I need to do with the calculator, so I'm going to pass back again.
Great, so I think it's your turn. So we would love you to have a go at trying this for yourselves. If you've got a calculator that would be really helpful. Let me put the slide back up with the equation to remind you what the equation is. So xn plus 1 is k times xn times 1 minus xn. And we'd like you to have a go at this. And if we all try with the same parameters, then we can have a poll and you can compare notes on your answer with each other. So we're going to suggest k equals 2. So the parameter is 2, and x0, the starting value, is 0.3. So if k is 2 and x0 is 0.3, could you then work out x1, x2, x3, and so on? So please give that a go. I'm going to put a poll up so you can vote for x2. Okay, so that's after you've done this twice. But you might want to keep going a bit further and see what happens when you have voted on the poll, okay? Okay, I'm going to show you the results in this poll. There is a very clear winner going on here. So I can even share that with you. So we seem to have a clear winner of 0.4872, which is what I've got written down on my piece of paper from when I did this earlier as well. A few of you have got a slightly different value, so maybe just double check how you're using the equation. Did you go the right number of stages? Did you remember all of the terms in the equation? Maybe those are the kind of issues there. So thank you very much for joining in with that. I am going to close that poll now. And let's have a little bit of a look at some of the suggestions that have been coming in of the longer term behavior when you're thinking about what happens for K is 2. So I've seen a few suggestions that it seems like it gets to a half. Seems like there's some interesting ideas going on there about trying to generalize that. So in terms of how changing the starting value of x0 affects it, how changing k affects it. Does your calculator cope with doing more iterations, or could this be a calculator issue? So there's all sorts of interesting ideas coming in there, which is great. Thank you very much for those. I'm going to hand over to Claire, who's going to think a bit about how we might think about this without a calculator.
Yeah, so the calculator is reasonably good, but if you want to investigate lots of different populations and lots of different values of k, it's going to be quite tedious. You can use spreadsheets, but what we've actually made is we've made a GeoGebra page for you where you can look at see what's going on graphically. So I'm going to share a GeoGebra page, and Charlie's going to put a link in the chat. I'm going to share it if I can find the share button. There we go. So hopefully you can now see a GeoGebra page that we've set up. When you click on the link, you may need to move some of these pieces around, and you may need to zoom in or zoom out depending on what size screen you're on. So I've got it here with k equals 2 and initial value 0.3. After 3 years, we're almost on 0.5. And you can see that after 30 years, we end up on 30 years, 0.5. So those people who are saying it converges to 0.5 are correct. What we'd like to do now is we'd like to give you a little bit of time to play with this GeoGebra file. You might find it's a little bit tricky to get the exact value of k that you want. So there is a second GeoGebra file where you can actually input a particular value of k. So with the first one, this is quite good for just moving around to have a look and see what's happening. If you want to investigate a particular value of k, then this one, say you wanted to investigate k equals 2.123 for some reason, you can put in your exact value of k. So hopefully we've got those two links in the chat, and we'd like you to have a bit of a play with that. And Vicky's going to give you some questions that you might like to think about whilst you're trying those.
So we've got 4 questions here for you to think about. You don't have to think about them in order. You don't have to think about all of them. You can pick whichever look most interesting to you. So the first is, can you find a parameter, so this is k, where the population dies out? The next is, can you find a parameter k so that the population settles to a constant value that isn't 0? And then question 3 is about, can you find a parameter rather so that the population eventually oscillates between 2 values, or maybe cycles between 3 values or 4 values? And then the 4th question, slightly different flavor, is why have we chosen that the parameter varies between 0 and 4? On that slider, or if you're using the slider version of GeoGebra, why have we chosen 0 and 4 as the lower and upper limits there? So what we'll do is give you a little bit of time to have a think about those questions and to experiment with the GeoGebra interactivity, jot down your ideas, scribble whatever you want on your piece of paper. And we will open some text polls in Slido so that you can share your ideas. So we'll do one for each question in turn. So if you've got ideas of question 3 or question 4 or whatever, just hold on to those for now and we will come to them. But let's just give you a couple of minutes of peaceful, quiet time to experiment with GeoGebra, see what ideas you come up with. This is great. I'm going to close that poll on question 1, and then I will talk you through some of the suggestions that people have been making there. Some of the ideas that people have been coming out. So I've been seeing suggestions like when k is 0.5, it seems like the population might die out. That seems a particular value. K is 0.44, k ranging from 0 to 0.48, 0.49. So there are a number of suggestions about that. Suggestions maybe if k is less than 1, the population always dies out. And suggestions about why that reasoning might be, maybe that the population is somehow always then shrinking. So there's a few different suggestions. Some people have been experimenting with different values of x0. So what happens if you start at a different value? What effect does that then have? And seeming that if k is maybe half or maybe k is less than 1, that it seems like it might die out with a range of different starting values. I'm going to hand over to Claire to talk us through that a little bit.
Yeah, I'm just going to share my screen again. Yeah. So hopefully you can now see the GeoGebra file with the k slider. So we've had people suggesting that if k is less than 1, that the population dies out. And this is true actually for any, oops, that was not good. I just deleted my slider, it's back again. That's actually true for any initial value. So if I take k down to less than 1, the population does die out. I think that was the first question, wasn't it? I'm just trying to remember, was I going to talk about why that happens at this point? I don't think I was I?
Yeah, maybe hold that thought and we'll gather some ideas on yes. Other questions for a moment.
Yeah, but I agree with all those. So I think we can now start to think about the second question.
Great. So I will open up another of these Slido polls where you can post your idea. And this question was about, can you find a parameter where the population settles to a constant value, but not 0? So not dying out like we just saw, but a non-zero constant value. And what could you say about parameters k that have that property? Let me talk you through a few of the ideas that I've seen coming in there. So seen suggestions that if k is less than 3, then it seems like the population stabilizes. Some particular values, 1.5, 1.8 coming up. Maybe if k is between 1 and 2, between 1 and 2.9 maybe. Some suggestions about oscillating for larger values possibly. So k between 1 and 2, k is equal to 2, k between 1 and 3. Those seem to me to be the most popular ideas coming in. Some slightly different suggestions based there. Some of them suggesting that specific starting values maybe has an effect. So that's really interesting. Claire, do you want to talk us through some of this with the GeoGebra again?
Yep, I'll just reshare the screen. Okay, so people have been suggesting numbers between 1 and 3. So k equals 2 is quite a nice number. So we can see when k equals 2, we go down to 0.5. That was the initial value of k we had. If we move k towards 2.5, we end up converging on 0.6. And again, I can change the initial value, and this always seems to end up converging to that value. Well, that's a nice big dip there. That's an example of where I started really close to the maximum number and lots of them died out because there's no food left, and then it came back up. And this one hasn't quite got to 0.6 by 30 years. And then as I'm going to just make that slightly smaller, otherwise it might get a bit interesting. As we keep increasing k, we can see that the actual number that it converges to starts to creep up. But we also start to go a bit more wibbly as k starts to increase. I think the next question we had to consider was talking about where it starts to oscillate. So I don't want to talk too much about that until you've had a chance to put in your answers. But we can see here, when we're starting to get up to k equals 3, it's starting to look a little bit oscillating. It's starting to go up and below a fixed value here, but there might be ones where it doesn't actually end up settling down.
Cool. So why don't we move swiftly on to that question about values where the population seems to oscillate. So either perhaps oscillating between 2 values, perhaps cycling between 3 or 4 values. So I'm going to open up a poll on that one, because some of you might have been thinking about that question already. So are there particular parameters k that you found where it seems like the population eventually oscillates between certain values. So there were some specific values I saw coming in, sort of various 3 point something, suggesting particular values within that, or possibly a whole range of values. Do you want to illustrate some of that for us, Claire?
Yes, I'll just share again. So some of the values we've had are 3.5 has been mentioned. No, not 3.5. Which numbers have been mentioned? I've lost the Slido. Let's try 3.3. So 3.3, we can see here that it looks like it's starting to ping between two different values. 3.12, again, there it looks fairly convincing, like it's pinging between two values. If you start to move up to 3.5, oops, I can't get the slides to get in the right place. Here it looks like we might have 4 different values that it's cycling through. So we have a sort of a maximum, a second lowest, a second highest, and a lowest that it's pinging through all 4 times. Did anybody find on the Slido anything where it oscillates between 3 values?
Yeah, I think there seems to be rather fewer people commenting on that one.
So I thought that if we take something in about the 3.82843-ish, I don't know if you can see it, but I think this one actually oscillates through 3 values. So we've got a high peak here, one down at the bottom, and then one in between. But it's really quite hard to see what's going on there. And that's quite a high accuracy value of K there.
Claire, can you just comment briefly on the significance of 30 years? Why are we stopping at 30 years?
There's no real significance as to why we're stopping at 30 years. We felt that was a nice number to start to see what's actually happening with the population. You could just keep doing this for as long as you like to try and see what's going on. Back in the 1950s, when biologists were using this to model populations, they didn't have the access to computers and things like we had in our days. So if they were looking at a population that seemed to settle down, it would probably settle down after about 10 iterations, and then they would stop. If it was one that was going a bit more interestingly all over the place, they would probably give up and start to do a different value of K. But now we've got computers that can handle this sort of thing, we can actually look at a lot more years. Okay.
Great, thanks. Why don't we have a quick look at the final question that we invited people to think about? So this was the one where we were asking you to think about why this slider for this parameter K goes between 0 and 4. What's the kind of significance of those? And I know a few people had thoughts on that. So if you could pop those in the poll on Slido there, we can have a look at those. That would be great. So lots of suggestions that this is maybe to do with populations becoming negative, possibly to do with the realistic nature of, is it possible for the quizzle that this would be a sort of plausible physical thing? Suggestions maybe it's to do with constraints of GeoGebra. I think the most frequent thing I saw was to do with populations being controlled, though.
Yeah, we can do a little bit of an investigation if we change the settings on the slider. So I'm going to change it to a maximum of 6 and get rid of that. Now, if I take the population above, GeoGebra doesn't break, but if I go above 4, we can see that yes, our population has become negative, which is a little bit unrealistic. And even if we start with a high population, it can still go negative right near the end. So the reason that that's happening is to do with the equation that we're using. So I've got here, hopefully everyone can see this, a Desmos graph. This purple line here is the equation y equals kx brackets x minus 1. So that's the equation that we're sticking our values of the proportion of population in. So if we start with an initial population of 0.3, we take that up to the kx1 minus x graph. I'm just going to take that down a bit. And then we want that to become our next value of x. The way we can do that is we then move across to the y equals x graph. This is now our new proportion. So repeat it, we can go towards the kx1 minus x graph, and then we can head back to y equals x. And if we keep doing that, show all my lines, we can see that for this value k, which is about 2.6-ish, it looks like everything's starting to converge onto one value there. And actually that value stays the same, even if we change the initial population. If we increase k a bit towards 3, it starts to look like we're stuck in a little square. And if we take it a bit bigger, it will tend towards a slightly bigger square, but I haven't got enough lines to show that. And that's where we're starting to ping between two values, and it's starting to oscillate. If we change our slider so that k can go up to 6, then when we stick in a value of x, then we could go to a new population which is bigger than 1, because the peak of this graph has now gone above 1. And if we go to somewhere that's bigger than 1, we can then end up heading down below 1. Sorry, below 0. So that is the reason for why we need to keep k less than 4, is to keep the population between 0, everything dying out, and 1, the total the maximum population that is possible. Okay, so I'm just going to hand back to Vicky.
Cool, thank you. I like how there's these sort of two different ways of visualizing what's going on. So one using GeoGebra to plot what happens each year with those initial graphs that you were exploring. And then also this Desmos one with the cobweb diagram, sort of different ways of visualizing what's going on. I think that's really nice. Let's think about the reality of this situation a little bit. So we've been sort of saying, well, okay, we've got the parameter, we know exactly what the starting value is, we can use that to then make a prediction for the population of quizzles a few years later. In reality, we never know exactly what the population is. We have to allow for the fact that there's a bit of uncertainty in that. This is the real world. There's uncertainty about every time we try to kind of estimate some physical quantity. We don't have an exact number. We could try to put error bars on it. We could try to say, well, we think it's this number, but we're pretty confident it's in this interval. And if you've got small error bars, you're very confident it's in a small interval. Sometimes it's much fuzzier data, we're less sure about what it might be. So let's explore a little bit how that uncertainty might play out when we look at this kind of GeoGebra visualization of this model for the quizzle population. So what we'd like you to do is experiment with how different starting values that are close together might or might not affect what happens. So I've got the slide up now with the equation with parameter k is 1.5. And let's imagine we know that x0 is, well, sort of 0.7-ish. Let's say we're pretty confident that it's between 0.6 and 0.8. So x0 is greater than or equal to 0.6, is less than or equal to 0.8. What can we say about the population of quizzles 30 years down the road? So what we'd like you to do here is have an experiment with different values. You can choose anything between 0.6 and 0.8 inclusive. You can have lots of decimal places. It's not just 0.6, 0.7, 0.8. Please have an experiment with different values of x0, and we'll collect some suggestions of what numbers you're finding for the population of quizzles after 30 years. What I'm seeing mostly coming up is pretty close to a third. So there's a lot of 0.33 something, and for some people they're saying it's a third, for some people it's 0.33 something slightly different, but pretty close to that. Is that what you were expecting, Claire?
Yes, that was what I was expecting. So I'm just going to try and share my screen, hopefully for the last time. So here you can see the the GeoGebra file again. I've put in 3 initial values, 0.6, 0.7, 0.8, and all of those values fairly quickly tend towards 0.3. Shall I very quickly investigate a different value of k?
I think that would be great if you could, Claire.
So as we're going up, we can see everything sort of tends together. But if I go up to something like 3.7, it looks like everything gets very different. Now that might be because our initial values, we had quite a large error on that. So if I instead knew the initial value was 0.7 to quite a high degree of accuracy, so if I knew that the initial value was between 0.699 and 0.701, we can see that these populations stay very, very similar for up to about 6 years, but then it becomes very irregular again, and we get very different behaviour in the different populations of quizzles. So if k equals 3.7, tiny changes in the initial population of quizzles, just 1 or 2 quizzles different, can have very different results in the number of quizzles after 30 years. Okay, so this was a very simple equation, but it can have very complicated behaviour for certain parameters, for certain values of k. And things like the weather also follow this sort of idea. Sometimes very different, very small errors in our initial measurements can predict very different weather a few weeks down the line. What I'd like to do now is I'd like you to pass back to Vicky, who's going to just talk a little bit about where else you might find these sorts of predictions.
Yeah, cool. Thanks, Claire. So we picked this example with the population because it illustrates so beautifully this idea that a tiny bit of uncertainty in the input value can have a really big impact in what happens, as with the weather. If you study mathematics a little bit further, you will have the opportunity to explore this kind of behavior a bit more. So the model that we've been using here is something called the logistic map. So you might have come across this phrase before. So this particular equation is the logistic map, and it's this discrete time one where we go from one year to the next. As you develop your calculus, as you go through A-level maths, further maths, you'll meet differential equations, which give a continuous way of doing that. And that's what we typically use for modeling all sorts of natural phenomena, whether that's to do with the weather and climate change, whether that's to do with population of species, whether that's to do with matters in medicine, whether that's to do with finance or the motion of the planets or all sorts of things. And if you go further, if you do maths at university, you potentially have the opportunity to explore those further, for example, through mathematical biology, which is a whole discipline. And at the start of this webinar, we had some slides showing you some of our colleagues in Oxford and Cambridge who use mathematics to make predictions in biology, in climate change and the weather, in other kind of settings as well. So there's lots more that we could say about that, but we don't have time right now. But we thought you might want to look into this a little bit further. So we'd like to give you an opportunity to do that. And Claire's going to tell us a bit more about that.
Yeah, if I could have the next slide, please. We've got a few ideas that you might like to explore further. So I'm not going to read them all out now because we don't have a lot of time. These are a few things that you could look at. We'd love to see your work. So if you go to the Enrich page with the ID number 14850, or you can go to Enrich and search for Maths Makes a Difference, and you should find the page. And you can send us your work. We don't want an entire thesis. 250 words would be brilliant. You can do a poster, you can do a bit of maths, you can do some pictures. Anything you like, really, and we really would be very, very pleased to see your work. We'd like you, if you want to send us something, we'd like you to send it in by the 28th of February, and after that date, on that page, we'll post what people have sent in, so you can see what everyone else investigated on these ideas. We are really running out of time, so I'm going to pass back to Vicky for a very quick wrap up. Got about 1 minute left.
Thanks, Claire. I'm really looking forward to seeing what everybody sends in. We've got over 300 people with us at the moment. It would be fantastic to see lots of ideas coming in. If you want to keep in touch with us, we've got social media. We've got lots of different social media things. We'll put these links on the slides on that Enrich page. You'll be able to access them there. Also, various projects that Claire and I and Charlie and Marilee and others of our colleagues are involved in that you might find interesting if you'd like to keep in touch with these things. This is the first webinar we've done in Maths Makes a Difference. We are hoping to run more. We would love your feedback. That would really help us to do that. There'll be a link in the chat and on the Enrich page so that you can fill that in. It's a super short feedback form. Any information you could give us would be really helpful. We really appreciate you joining us today. We hope that you will follow up with the page on Enrich and sending us your ideas. We're looking forward to seeing that. Thank you very much for joining in and for getting stuck in with the mathematics and for sharing such great mathematical thinking with us. We really appreciate it. That is it.
Yeah, if you want to say, sorry, just going to say, if you want to save the chat, so you've got all the links saved for you, then that might be a good idea to do that. And thank you very much, everybody, for coming.
That is it. Thank you, everyone. Take care.